Good afternoon, ladies and gentlemen. Welcome to this week's Engineering Science and Mechanics Graduate Seminar. Our speaker today is Professor Ji Wang from Rensselaer Polytechnic Institute, where he is the Clark and Crossan Chair Professor and Director of Biomedical Imaging Center. So, as you can probably guess, he is heavily involved in imaging and biomedical imaging. And the particular form of imaging that is his forte is computerized tomography. Now, I bet many of you have undergone such a procedure in a hospital. And when I was a graduate student, that's when hospitals began to have some equipment like that, some hospitals. And it used to take very, very long to do a scan. Nowadays, you can get scans done in 5, 10, 15 minutes or so, many times. Okay. So part of the reason why scans can be done so quickly is because researchers like Professor Wang have been finding out optimal ways of scanning whatever object is being scanned. And he is going to tell you much more about it in detail. Professor Wang, please.
Thank you so much, Akhlesh, and my great pleasure having this opportunity to present computed tomography work. And I will basically talk about 5 points. And start with background, then we talk about 3 things. And the third is spiral scanning, interior tomography, and also robotic scanning. So just put it together, you will see how this technology is being developed into future. Okay, so first chat a little bit about background. And as Akhlesh mentioned, many of you show maybe also scanned by CT scanner, look like this. So this is a picture I got from GE, General Electric. GE happens to be my first name. So we collaborate with GE for over decades. So we do a lot of nice things. And the CT scanning is important. And I read some new statistics, and about 200 million scans a year nowadays. And in the future, I read some also news articles talking about the number of years and maybe 1 or 2 decades down the road. And each person and each year we get 1 scan. And some companies say 1 by 1 by 1. So that means just a huge societal health care impact. So very important. So what's going on inside the CT scanning? How come you're lying on bed and a few minutes, actually a few seconds later, we got all the information about the internal structures. So this is certainly a magic vision, exciting story, a simple version, a TED lecture. So I once prepared one, and this one recently, I just double check, we got over 1 million views. And about 10 minutes, you see rough idea how things going on, and there are some dig deeper materials in it. And so this is really popular science talk. So you just watch it, you got a superficial idea. You still kind of know what's going on, not really. And now for this lecture, we have a well-educated faculty colleagues and students. So I gave an enhanced version of this CT story, okay? So background-wise, first, we want to ask what is X-ray? So X-ray is electromagnetic waves, so within certain wavelength range. And the range is such, it's around nanometer plus minus 1 or 2 order degree scaling. So in that sense, so the wavelength is nanometer. So many people are talking about nanotechnology. So century ago, we got this X-ray imaging technique that is nanotechnology. Okay, very cool. So we know X-ray is one kind of electromagnetic wave, and we know X-ray has duality. It could be viewed as a wave described by Maxwell equation, and also could be viewed as particles. So in our laboratory, use photon-counting detectors, so we can count X-ray photons one by one in energy discriminative fashion. And also we can measure X-ray wave interference. And really, this is a picture of laboratory system. We finished this project 2 years ago, supported by a NIH R1 grant proposal. So with one scan, small animal scan, so we could acquire 3 contrast mechanism data. So first is attenuation, so utilize particle nature. The second is so-called differential phase contrast imaging. So you really map the reflective index distribution. And also we can do small angle scattering called dark field really scattering imaging. The signal in the dark field image is very sensitive to determine nature of nodules. So we can tell difference from malignant and benign tumors. So we have been working on this so many years. And what's the fundamental idea? So think about X-ray beam or wave propagating horizontally. Then you got a thin layer of material here. So then we ask a question. So you got incoming radiation, the flux I in. Then you got a little bit attenuation, you got I out. So differential change, first order derivative, and as you can expect, is proportional to the incoming intensity. So this is just exponential attenuation process from this differential relationship. So you got this differential relationship and the coefficient mu, and is what we call linear attenuation coefficient. First order differential equation, you solve this equation, you got this so-called Beer's law here. Okay, you can measure input flux, you can measure output intensity. So you do the ratio, you get a log. What you have is this linear integral with respect to linear attenuation coefficient along the X-ray path. So this is differential relationship. This is in the integral form. You perform data pre-processing, and what you can measure, because I in, I out quantities you can measure. So what you can measure is a line integral. Line integral in discretized case is just the resum multiple unknown pixel or voxel values added together. So you got the linear form of measurement. So this is the imaging physics. So computed tomography is nothing but reconstruction of cross-sectional image from X-ray data. And as I mentioned, the X-ray data are just the line integrals. So along, say, these parallel X-ray path lines. So this defines one projection consisting of multiple line integrals. And this projection is characterized by projection angle. And you can keep changing projection angle. You get various projection profiles. You put them together, you got sinogram, two-dimensional sinogram. One variable is detector location, T. The other variable is projection orientation, theta. So that is a two-dimensional function. We call it sinogram, and the two-dimensional function is obtained from underlying image f of xy, also two-dimensional function. So you use X-ray imaging physics measurement, you got data. And the computed tomography is an inverse process from data to underlying image. Then how you can invert this process from sinogram or projections or line integrals, how you can go backward to reconstruct underlying image. So this is interesting. And before I explaining method to do the inverse problem, and I would say, and just like X-ray and has dualities, wave and particle, we can view information in duality. And so we say the information like image, picture, signal, and can be viewed as a collection of pixels or voxels. So each pixel is a particle, is element, and the particle pixel is uniform, characterized by mu. So different voxels, you got different mu values. Just try to solve for pixels, pixel values or voxel values. On the other hand, the image can be viewed as a superposition of different sinusoidal waves. So that's just an easy way to say Fourier analysis, right? So corresponding to these 2 point of view, and we have 2 kinds of reconstruction methods. So we first say the picture consists of pixels, okay? Then we say the picture can be viewed as a superposition of many sinusoidal waves. So this is a Fourier spectrum as any element in 2-dimensional Fourier spectrum give you a 2-dimensional wave propagating along certain direction at a given frequency with a phase and amplitude, okay? So sinusoidal wave are building blocks here, just like pixel voxels are building block for digital picture. So corresponding to these 2 point of view, so we can have 2 types of image reconstruction algorithms. So first, we have algebraic or iterative algorithm. So this is from a particle view of information or images. So we convert X-ray data into line integrals to form a system linear equation. Then we try to solve linear system linear equations. So system of linear equations can be solved. So this is nothing surprising. And we learned that in high school. And let's deal with a 2x2 image like this. So you perform horizontal measurement, you got 1 rays, you got 2, you got 1 rays, you got 1 linear equation. You got a second linear equation. Altogether, you got 4 rays, you got 4 linear equations. The whole system, you got 4 unknowns. So roughly speaking, you could solve the system of linear equation for unknowns. That is image reconstruction in this case. Certainly, you need to make sure all these measurements are independent and they have sufficient number of independent linear equations to solve the system. 2 horizontal rays, 2 vertical rays, as I shown earlier, not enough. Usually, you get another ray. Make sure you got enough information to guarantee unique solution. And how do you solve the system when the number of unknowns is not huge? You can solve using classic techniques. But for medical imaging, and typically we solve 512 by 512 array, image array, and you try to reconstruct the image volume and many slides. So the number of unknowns is just too huge to be inverted practically. So we use iterative algorithm. So essential idea of iterative algorithm is just to make initial guess. So think image just nothing there, 0, 0. Then you, based on your initial guess, you do retracing. You get synthesized the line integral. You compare your theoretical prediction and the practical measurement. You see discrepancy. You redistribute the error along the X-ray path, and you can correct the errors for vertical projection direction. And then you just compute horizontal projections according to updated image. Then you see discrepancy again. Then you do the same trick. You back propagate error over the field of view, and each iteration give you a little bit better results. So this is a rough idea, linear system solution. Okay, so the measurement ought to be independent, give you information. And also you may wonder, even you shoot all the X-rays through the object, will you have enough information to unravel the image matrix with the information? And the answer is yes. Let me just explain this idea using this simple diagram. And we think image pixels are all just triangular shape. Then we use a unimpeding strategy. And so for the outermost layers, so the orange pixel, so we shoot one ray, and then we can measure incoming intensity and just the output, just the photons escape the attenuating background. We can do measurement. We know the input, we know the output, we apply Beer's law directly, and you can estimate, we think this triangular pixel is homogeneous, so characterized by constant mu. Then we can use Beer's law to solve this yellow mu. And likewise, all the yellow pixels can be solved with peripheral X-rays. So after that, we look at next layer, this green pixel. So we have incoming intensity we can measure, and we know this orange region already. Then we can compute what will be real income to the green pixel. Then we know the incoming intensity. Likewise, you can measure intensity here, and with a known attenuating background, we can infer what is the output and at this green pixel boundary. Then we can turn around and solve for mu of these green pixels. So that is to say we can solve for all these green pixels. Then you move on to next layer. So layer by layer, you can solve all the object. In other words, you can understand if we are dealing with a two-dimensional reconstruction problem, and you arbitrarily draw a line through the object. Along that line, you have line integral measurement or X-ray measurement. If you arbitrarily draw such line, you always got data. That's the maximum amount of data you could get. According to my unimpeding ideas, that is sufficient amount of data with which you could uniquely solve the image reconstruction problem. And we can extend it a little bit from 2D to 3D. And for 3D imaging geometry, and we can use planar integral instead of line integral. So you have a bunch of line integral, you add it together. That's a planar integral. And you can just make a similar statement. If you have a spherical object, you arbitrarily draw a plane cutting through the spherical object. Then you have planar integral measurement. You have all such planar integral measurement, and you have a sufficient amount of data to do 3D image reconstruction. So that's just the particle point of view. And the complementary point of view, and we call it analytic Fourier prose. And that is a wave perspective of image reconstruction. So let me tell you the key central theorem called Fourier-Slice theorem. This is the key behind analytic image reconstruction. So you have a two-dimensional object, f of x, y, same thing. So you make one-dimensional parallel beam projection, p of theta t, and theta is fixed. And we perform one-dimensional Fourier transformation with respect to variable t. You got a one-dimensional Fourier spectrum. So that Fourier spectrum, and is the spectrum along this radial line that make same angle in the two-dimensional Fourier space. Capital F of UV is Fourier transform of f of x, y. So this is called Fourier slice theorem. So with one parallel beam projection, you got information along a radial line in two-dimensional Fourier space. If you keep changing projection angle theta from 0 to 2 pi, this line will sweep over the whole domain of Fourier space. So then you will have enough information to perform inverse Fourier transform and reconstruct the underlying image. So the Fourier slice theorem can be analytically proved, but heuristically, and just look at this picture, you can appreciate why you have Fourier slice theorem without any mathematical derivation. And you think the image is just a summation of many two-dimensional wave field, say special case. So you got a bunch of horizontal waves, okay, as building blocks of your image. So think about parallel beam projection. If you shoot rays vertically for this parallel, for this horizontal wave field, so along this line you get highest value. Along this line you got a minimum value. So with the vertical projection, you do capture some information about horizontal two-dimensional waves. Okay, very good. So you have information about underlying image. How about I collect projections from orientations other than vertical one? So you shoot a ray, so going this way, or you just shoot a horizontal ray. What will happen? Think about it, and you will first see the positive cycle, then you see negative cycle. So these sinusoidal waves always got a positive and a negative. So you add them together, line integral process. You add them together, you cancel out positive and negative contributions. You end up with 0. That is to say, and the projections and along a oblique orientation, horizontal orientation, wouldn't give you any information. So I already explained why you perform Fourier transform for one-dimensional projections only give you projection the wave field along this direction. So this direction is perpendicular to this wave propagation direction. Is perpendicular to the X-ray projection direction. So this Fourier slice theorem is geometrically clear, as I shown here. A filtered back projection algorithm is well known. That is nothing but inverse Fourier transform in polar coordinate system. So with filtered back projection algorithm, so we can get crystal clear images and a very powerful technology. So it just covered the background. What is image reconstruction and the two approaches for image reconstruction. So scanning mode, very important. So parallel beam geometry, and you collect pencil beam data one by one, and not very efficient. So you keep modifying imaging geometry. So instead of using one source point, one detector, we can use one source point mini detector. So this is a fan beam geometry. And also, when you collect data, and you should rotate source and detector ensembles around the patient. At the same time, and you could translate the patient continuously into the gantry. So this is a helical spiral imaging mode. And the detector can be expanded from one-dimensional detector array to two-dimensional. Then fan beam becomes a cone beam geometry. So the first helical cone beam CT scanning, really micro-CT scanning system was prototyped in University Buffalo, and we did the material research to image rod shape or planar-like specimens. So for rod shape samples, so we designed this helical scanning geometry. So this is the first system. And the helical cone beam geometry later on turned out to be very important for medical imaging. And how to perform image reconstruction and is not a trivial thing. So so-called time window and the pipeline is set any point and in the object. You can make a line and with two ends on the helical trajectory, and the detector array is defined by upper and lower helical turns. This is called time window. The nice thing is that if you use time window, so you arbitrarily draw a plane. You see this case, you have multiple triangular shape. You have a perfect data mosaic pattern. And to cover that plane, that gave us data to estimate planar integral. So you arbitrarily draw a line, you can do such approximation. Then we can try to give very good reconstruction results. And I wrote a paper, 91, that method is only approximate. It took a field over a decade to derive theoretically exact cone beam reconstruction algorithm. This is also known as Katzowitz algorithm. And in collaboration with Katzowitz and others, and we extended the work, and we considered triple source scanning. So with this triple source scanning geometry, and you got red cone and the green cone, blue cone, you still have this nice mosaic pattern to perform very efficient, theoretically accurate cone beam reconstruction. So the evolution from fan beam to cone beam is to collect more data so you can improve temporal resolution. The triple source spiral helical CT geometry really made a step forward and just collect the cone beam data in parallel. So anyway, so this is the first topic I want to cover. The second one is interior scanning. All the trouble with helical cone beam scanning is the beam divergence and the longitudinal data truncation. So that make theoretically exact reconstruction very challenging. So symmetric to the helical cone beam problem, and we also deal with an interior tomography problem that involves transverse data truncation. What I mean, you see here, and I just show you fan beam imaging geometry. The fan beam covers the object completely. And my heuristic argument, we do unimpeding. So we need all the rays to resolve outermost layer, then next layer, then layer by layer, I solve all the problem. And then now the interior problem, it just got data. And the X-ray beams only go through a small region of interest inside the object. You do not have peripheral rays to peel the onion. So this is a much more challenging problem. And the conventional wisdom has been that interior problem does not have a unique solution. So this is well known. And since 2007, my group and the peers group revisited the problem. And we found an interior problem actually could give you a unique solution if you twist the problem slightly. And we introduced the prior knowledge. Say, inside the region of interest, we have a small sub-region of interest over which linear attenuation coefficient is known. For example, air in airway, blood density in aorta. So some small region over which we have perfect knowledge. Then we go through Hilbert transform analytic continuation. We show the interior tomography interior problem can be uniquely solved. Then we got some critique. And some reviewers and peers say, and you assume known blood density, but for cardiac imaging, you know what? And you inject contrast material, blood density is changed, is unknown. How do you deal with that? So we spent about 2 years and we present a sparsity model. We assume a region of interest consists of a limited, finite number of piecewise polynomial region. It's just like a band limitedness assumption for classic signal processing. So based on this prior knowledge sparsity model, we show interior solution is unique. And later on, we also add stability to our theoretical analysis. And the sparsity model is closely related to compressed sensing. So many medical images and natural images and has a sparse representation. That's why we can do image compression. And the old way you do wavelet analysis, relatively new way, and we use deep neural network and do auto encoder. So you have encoder, you have decoder. This is a nonlinear PCA analysis. You have a hidden latent code and compress the signal and into much shorter code. So that allows interior tomography as well. So we can do interior tomographic reconstruction requiring data fidelity term that defines a quadratic trajectory. So somewhere here. Then on top of that, we ask underlying image is sparse or transform of underlying image is sparse by minimizing L1 norm. You see the L1 norm and is minimized and subject to data fidelity term that give you sparse solution. If you use L2 norm, so the intersection will be generally somewhere here. So got a non-zero component value. But for L1 norm, as shown here, and you only got sparse solution in majority cases. This is not only a mathematical curiosity or theoretical analysis. So we performed experimental study, and the real data show, and you only need pseudo X-ray going through region of interest. Even the region of interest is off the center. You use X-rays going through region of interest only, then you can reconstruct the profile and in great agreement with global data reconstruction. And if you just assume linear integral, and there will be some problem because real data is not monochromatic data. Really, you use polychromatic X-ray beam. So we can use a nonlinear model to perform interior tomography. Then the old and the new method show significant improvement over old method. Old method you assume line integral. The new method assume just the nonlinear model taking polychromatic X-ray spectrum into account. So this is what we have been pushing forward. And with interior tomography, and earlier I mentioned we could use 3 X-ray tube to perform triple source helical cone beam scanning. Now with interior tomography, and we can put more minimal X-ray source point, but the larger number of X-ray tubes and the smaller field of view, smaller detector panel. Otherwise, you do not have space to fit into a donut-shaped contract. So in this case, and with interior tomography, we can indeed target a small region of interest, like a plaque in your heart, like a stent you want to characterize. So this is what we call multi-source interior tomography. So you really perform data acquisition, not only along one-dimensional array, so all points collect data simultaneously, not only just the cone beam, so you got 2D data acquisition. So now you got this angular dimension. So we collect all the cone beam data simultaneously. So in the limiting case, this can allow you to perform instantaneous interior image reconstruction. So the temporal resolution will be perfect unless you can just do faster than speed of light, which is at this moment not possible. So each time you got one region of interest mapped, then the things may change. Then you can just zoom the imaging aperture to another place. And for each region of interest, you focus on that region of interest. You can use a high resolution detector, so you can zoom in. And if the ROI is not large enough, you can roaming around. So the scanning with interior tomography becomes zooming and roaming. So that is something we think quite interesting. So the third point, we talk about robotic scanning and CT scanning mode. I explained a number of them: parallel beam, fan beam, cone beam, helical cone beam, multi-source. So all these developmental ideas are driven by the need of faster imaging speed. And for several decades, CT image resolution and not much improved. It has been about 0.5 millimeter for, I think, at least 20 years. And very recently, Canon used a high resolution detector. Then we got improvement, something like between 200 to 300 micron high contrast resolution. So ultra high resolution is critically important for inner ear imaging, plaque characterization, and tumor analysis, so on. So more than decades ago, we proposed an idea, we call it a clinical micro-CT to deliver ultra high image resolution in patient and with cochlear implantation, temporal bone imaging as a main example. And I wrote R01 and not got good enough score in gray area, not got funded. So more than a decade passed, and today we see some newer technology. First, traditional X-ray tube emit polychromatic X-rays, different energies, and you use energy integrating detector. So this is color blended. That's why you go to hospital, you see black and white CT images. And the latest technology, we use a photon-counting detector. You detect each individual photons one by one. And also you know the energy level. So we can know the X-ray photon is of soft X-ray or hard X-ray. And we can put X-ray photon we just detected into the corresponding energy beams. So we add spectral dimension to X-ray measurement. Then we can reconstruct colorful X-rays, CT images. So this is the benefit of photon-counting detector. Equally important, you not only have spectral information, and also you can make detector element much smaller. So right now, the New Zealand photon-counting detector with a pixel 55 micron, and you can use it in 2x2 bin. You got 100 micron resolution. So this kind of detector element allows us to significantly improve clinical CT image resolution from current resolution, the best around 200 millimeter. By several folds, we can target around 50 micron. So this is micro-CT resolution. So photon-counting detector is an enabling technology. And also when you do such small region of interest imaging, interior tomography, you don't know where the region of interest. It's case by case. So we see the robotic arm micro-CT system, our industrial partner, Redelectica, is closely collaborating with us. So this is for animal. So we are working on to build a human system. So something like this. So you perform helical CT scan to get a rough picture. Okay, rough picture first place. Then we do quick AI-based analysis. We know region of interest. Then the patient lying on the bed translated into this clinical micro-CT scanner. So two robotic arms hold the photon-counting detector and the micro-focused X-ray tube and orbit around the region of interest. So we save radiation dose and we fuse spiral cone beam CT and interior tomography together, and the clinical resolution and ultra high resolution, and to provide information otherwise impossible. So right now, the clinical CT resolution is not sufficient. Like temporal bone surgery, oftentimes you need to open up to make sure the nature of disease. We hope with clinical micro-CT, we can do a whole lot more. So this is the third point. So spiral scanning, longitudinal data truncation, interior scanning, transverse data truncation, robotic scanning for clinical micro-CT, and integrating spiral CT and the interior tomography. And what's the feature? What's the future? The future, and since 4 years ago, and my group has switched from classic image reconstruction research, analytic formulation, iterative algorithm, and we switched to data-driven image reconstruction. So we wrote a book last year, and over 400 pages, machine learning for tomographic imaging. So several years ago, you ask imaging researchers, how many kinds of image reconstruction algorithms do you have? The answer will be, okay, analytic, iterative. Just I explained to you. And with deep learning, so we are adding the third category of image reconstruction algorithm. We call it deep image reconstruction. So we use neural network to do image reconstruction. So a lot of things, and we don't have time to explain deep image reconstruction. But anyway, with high power of deep learning network, and we can do image reconstruction much better. And also we can use portable, cheaper hardware components, make image still good enough for diagnostic quality, like portable, movable, mobile CT scanners, wearable PET camera, and just recently you may show the news called hyperfine small MRI scanner. You can just move it around to patient bedside, and also portable ultrasound transducer. So with all these things, machine learning will help, and for imaging and diagnosis. Of particular interest, we want to build a C-arm machine to perform X-ray imaging and also generate not only X-ray projection, also MRI projection. So we got a permanent magnetic field, made it up. So each time you got X-ray projection image and also MRI projection image. And the C-arm do the rotation, and we translate the patient. You can perform double helical scanning for simultaneous CT and MRI imaging. So this is a project we are still working on, okay? And the future, look into future and step further. So we believe this is just a kind of vision, and we believe the future medical imaging will be well connected and decentralized. And the trend is justified and as follows. So just like old days, we have bus station, we still have bus station, but then you mainly rely on your car. And now the Uber, okay, and we have big mall. And now we have Internet of Things, door-to-door delivery, and for banking system, now you have Apple Pay, and in the future, Bitcoin. So all shows what I just mentioned here. Civilization spanned by both mobility and connectivity. As to medical imaging, so right now medical imaging facility is a centralized one. So you make appointment, you go to their department of radiology or imaging center. The future, and we imagine we do something called avatar. I will explain next slides. So with that imaging service delivered to you, patient centralized Internet of Things will become Internet of Service, like Internet of medical imaging service. Avatar is a name I made, meaning auto-driving vehicle-based affordable tomography analytics robots. So just think, you have auto-driving car, you call it up, and in the car, you have a portable imager, do CT, MRI, ultrasound, everything. And you do the imaging on spot in your home or just the battlefield or natural disaster scene. So you got imaging done there. Then also you perform automatic analysis. So this will be future, I believe. So pretty much this is my presentation. Those of you interested, you could read some review articles we wrote, like helical scanning. So I got this review article published covering hundreds helical cone beam classic papers. And just the key point for interior tomography, and we have a review article entitled Meaning of Interior Tomography. And for data-driven deep learning AI-based reconstruction, I wrote a perspective on deep imaging 2016. So that's the first perspective. I outlined how the field will emerge, will be developed. And recently, we were invited by Nature Machine Intelligence. We wrote a review article on deep learning for tomographic image reconstruction. The full paper will appear in December this year. Thank you very much.
Great. Well, thank you, Professor Wang, very much for a delightful and informative introduction to scanning, to scanning tomography. And the floor is now open for everybody to ask questions.
Thank you, Dr. Wang. With regards to scanning the heart from a high resolution standpoint, does the new technology have the capabilities of viewing, say, mitral valve motion or heart motion, where in the past, I believe you needed to be stable and still? Over.
The current cardiac imaging technology is fantastic. They can do a lot of things we couldn't imagine years ago, but still the image resolution is not good enough. Like the plaque characterization, we cannot do it with medical CT. Like stenting, if any race stenosis, and we cannot judge reliably. So higher resolution still needed, but the cardiac CT technology is updated every year, and we hope we could improve spatial resolution by 5 times, for example. So this is something we are working on.
Thank you.
Other questions? So, Professor Wang, can we use the same idea for the same type of an equipment, for example, to sense not only living objects, but also dead objects or never alive objects? For example, can we go through a meteorite?
So the technology can be extended to other domains. And we mainly focus on medical imaging, but sometimes we also involved with material characterization, like a nano CT scanner. I worked with a company, California-based company called Sinusoidal, and so we have some material research going on. Also, a European company, they use Micro-CT to characterize dynamic process, like just some material dynamic process, like a phase transition, and see how the process going on. Then you need temporal resolution as well. And so we try use deep learning method to remove noise when you have very high imaging speed, and the image tend to be very noisy. So we are working on all these things. So just too many possibilities, and that is generally related to the inner vision, and we can usually perform superficial observation. But when you want to see inside, and in many fields, and like what's inside of the Earth, so you want to do Earth tomography, and you want to just do tomography of, and say, black hole. So all kinds of ideas, but my expertise is mainly focused on medical imaging or small animal imaging.
I see. Okay. Questions?
So with the Avatar project, with the autonomous vehicle with the scanning inside, would the idea be that the patient would sit in the seat of the car and get scanned there?
This is up to our imagination. I think ideally, if patient is able to move, the patient can walk into the car. Otherwise, say I can imagine a robot sit in the car, it will walk out. So meet a patient. So this is really yet to be defined domain.
Thanks.
If you are interested, so this is the URL. You click here, you see my white paper and a few related articles you can read, and we welcome collaboration. So I just enjoy doing multidisciplinary collaboration. So it's interest driven. So anything we feel cool, we just explore together.
Wonderful. No more questions? Well, in that case, let us thank our speaker. And Professor Wang, you and I will continue to chat after a while, but we'll let the students go.
Thank you. Thank you very much.
Please. Yeah. They can't clap. Sorry. No, that's the problem with this. Yeah, there's.
So Akhlesh, I'm really